In this little video, I'm going to talk about something called the wave equation, which is commonly used to describe one of the most fundamental equations that you'll meet in GCSE physics in terms of waves. And it's to do with answering a problem of if you have a source of waves that are being generated from a place, and you have a person who is receiving those waves. So let's imagine these are sound waves or so on. We're interested in answering the question of what is the speed of the waves as they travel. Now, you can do something in terms of speed, distance over time, and try and measure the time it takes from turning on your speaker to somebody hearing it. And so it is possible to do, but in terms of a more sort of series of fundamental measurements of what we know of waves, what is it that we can deal with? Well, let's think of this in a slightly different way. And let's imagine that we have a train. Five carriages, and probably shouldn't have gone to all the travel. What amazing artwork this is. I've made a steam train. And you've got a person who is watching it. And so this train is just going to go past him. Now, let's say this person knows that the length of a carriage, they're all the same, and the length of the train itself as well, and they are all 25 meters. So all of them are 25 meters, and they count, and in 1 second they see 3 carriages go past them. So they know the following. The length of the carriage is 25 meters, and in 1 second they count 3 carriages go by. With that information there, how fast is the train going? And you might think, okay, yeah, that's fairly straightforward to work out. They have 25 meters, and there's 3 of those in 1 second. So that tells us that 1 second, so it starts off there, and 1 second later, we're there. And so that must mean that the whole train has moved 75 meters in 1 second, which gives us a speed, therefore, of 75 meters per second. And you might think, fantastic. Other than your amazing artwork, what has this got to do with waves? Well, these are all analogies for things that we know about waves. If we instead of this being a train, move this back. Oh dear, I've moved the person as well. Unfortunately, I have removed this person's head. Oh dear. Let's give them their head back. Instead of it being a train, let's make these waves. So we just have waves of wavelength Okay, we're ignoring the connector bit, but the waves are now wavelength of 25 meters. So this is an analogy of the wavelength. And this second thing, the number of carriages that go past in 1 second, well, that is the same as the frequency. How many waves go past a point in 1 second? And for the train, all we had to do was do 25 times 3. And therefore, what that tells us is that if we think about this in terms of a wave, the 25 is the wavelength, lambda, the 3 is the frequency, f, and multiplying those two things together gave us the speed. And that is how we get the speed of waves. It's what we call the wave equation. So you don't need to write a whole load of stuff about this, but this is what we do need to know. So if we know the wavelength and frequency, so wavelength lambda and frequency f of a wave, we can calculate its speed with the equation wave speed equals frequency times wavelength. And your normal units for this would be wave speed measured in meters per second, frequency is measured in hertz, wavelength measured in meters. With symbols, this is often written as V equals F times lambda. And that's what's called the wave equation. Now you might think, wait a minute, I know another equation of speed, and it's speed as distance over time. And in many ways, these are the same equation. This is actually the same equation as speed as distance over time. It's just written in a slightly different way. And to think about why that is, we need to consider a second relationship. So this is one, by the way, this is an equation you have to remember, but we have to think of the relationship frequency and time. So let's think about the definition that we had for both of them. Okay, so time period is defined as the time taken for one wave to pass a point. So if we go back to our little sort of example here, if this person, rather than for time for 1 second, was just timing how long it took for one of them to go by, they'd start a stopwatch and they'd start their stopwatch and then they'd stop their stopwatch, and they would have a time for one wave to go by. Okay? And that's measured in seconds. The frequency is the number of complete waves to pass a point in 1 second, measured in hertz. So what we have there is this idea of saying there, you start your stopwatch, you time it for a second, and you see how many of these waves sort of pass you. So what you do in that case is you start your stopwatch, and then after 1 second you stop it. And then you say, right, how many waves have passed me? Those two measurements are two ways of deriving the same, they're kind of telling you the same piece of information. They're the reciprocal of each other. Because let's imagine that we have if we say a wave and we measure the time period of the wave and we find that it's 0.2 seconds. Okay, so a wave has a time period of 0.2 seconds. Well, what does that mean? How many full waves are you going to see? Okay, what's going to be your frequency in that case? You may be able to see where this is going. But if you kind of have an entire, we've got our sort of person who is measuring it. Okay, so there's our start point, and let's see what they will, undo that, don't need that, the wrong thing. What are they going to measure? Well, what they will do is they'll start their stopwatch. After 0.2 seconds, 1 wave has gone by. 0.4 seconds, 0.6, 0.8, 1. So after 1 whole second, you move there. 1 whole second, what we'll find is that 5 whole waves have gone past. This will be the number of waves. 5 waves have passed that point in 1 second. And so what that tells us is, how is 5 related to 0.2? Well, it's just the reciprocal of it. Okay, because the number of waves in 1 second is equal to 1 over 0.2, because that's your 1 second divide. This is your total amount of time. This is how many waves in each, how long for each unit of waves, and that will give you 5. And that's how the two things are related. This is our frequency, this is our time period. So what we end up with is this relationship of frequency when measured in hertz is equal to 1 over the time period when that is measured in seconds. Or, as in symbols, F is equal to 1 over T. Now this is an equation that you are given in the exam. So it's a given equation. It's one that you don't have to remember, but you do have to know how to use. Similarly, you can swap it around by multiplying up through by time period and dividing through by frequency, and you'll end up with the opposite of that, which is time period is 1 over the frequency. So the two things are, that's how the two equations are generated. Now, if we think about what this means, given that frequency is 1 over time period, if we think about what it means for our equation V equals F times lambda, well, frequency is just 1 over time period. So you could substitute in 1 over time period into here instead of having the frequency there. So you get the speed is 1 over time period times lambda. And that ends up with looking like, if you just make it a bit neater, you get wavelength over the time period, or you get the distance of one wave divided by the time for one wave to pass. Or, to be more precise, you get it distance divided by time, which is speed. Exactly why they've decided to, with waves, we decide to work with frequencies as opposed to time periods. It's just a decision that was taken. So there's no fantastic reason that I know of it intuitively, but it does just lead us with this idea that we just tend to, by sort of convention, use the relationship V equals F lambda rather than V equals lambda over T. That tends to be what we use. And these two equations, V equals F lambda and F equals 1 over T, are the equations that you can use to determine the speed at which waves are traveling. Here's the example. We've got a stone that's thrown into some water, and in 12 seconds, 8 waves are counted past a point. The wavelength is measured as 0.45 meters. What is the frequency and what is the speed? You can give yourself a quick go of that if you want. So let's work it out. Okay, so step 1. We want to know, given that in 12 seconds we have 8 waves, we want to know what do you get in 1 second. So 12 waves in 8 seconds. That is therefore going to mean that if we've got 8 seconds, we divide it by 8 to get to 1, so that means we'll get 12 over 8 in 1 second, which is therefore 1.5 waves per second, or 1.5 hertz. So that is F. And then we can say, right, part 2, what can we get for the wave speed? Frequency times wavelength. So we've got 1.5 hertz. And in this case, we've got a wavelength of 0.45 meters. Which is 0.675 meters per second. Something that I was going to write for that example and I've forgotten. We can also say, what is the time period? My pen's just run out of battery. And we can therefore, for part 3, we can say that T is equal to 1 over F. So that's going to equal 1 over 1.5, which is 0.67 seconds. And there we go. And obviously we should get, if we decided to do it by distance over time, we should get that if we did speed is distance over time, we would do, in that case, we would do distance of 0.45 over time, which is 0.67. Which again, we get 0.675 meters per second. So doing it that way, you get exactly the same answer. Just be aware that if you do 0.67, you'll have rounded slightly because it's one of those horrific things that's a never-ending number in your calculator. But that's how we use the equation, and it's just various different setups of picking out the information in different ways and